Hello, today's space engineering lecture is a case study, the TransHab, the transit habitat that I worked on at NASA around 1997 through 2000. So what is TransHab? It was an inflatable prototype module, and it revolutionized the way people think about designing and building habitats for in space or on other planetary bodies. The TransHab concept was originally designed as a lightweight inflatable habitation module for space applications. Originally, a Tiger team with Dr. Bill Schneider, who now teaches at Texas A&M, we came up with the idea in 1997 for a lightweight habitat module for a human mission to Mars. And so really it was with the transit habitat, which became TransHab, transit habitat, for this idea. And so one of our goals was to be able to launch in the shuttle payload bay a module that would give us enough volume for the mission to send 6 crew to Mars. And so that needed more than just one space station module. You needed about 200 to 300 cubic meters of total pressurized volume, not net habitable. But, and so that was the idea, the premise behind the transit habitat or TransHab. The design was liked so well by JSC and other centers and then headquarters that they proposed to use it as a module, a replacement for the Habitat module for the International Space Station. Now, the Habitat module was supposed to have been built by Boeing, but with the overruns and cost overruns of space station, that was placed on hold, and they were taking the functions of the habitation capability for humans and putting it and spreading it out throughout the rest of the modules, the lab, nodes, and so on. So the TransHab module actually became wildly successful. Popular Science published a whole article about it from the standpoint of space hotels in 2010, because Bigelow had purchased the license for the patents to use the technology. And in 2017, many years later, it won Government Invention of the Year. The beam, the Bigelow expansion module that's on ISS, is a direct result of this work. So what was the vision, mission, goals, and objectives of the original Mars Transit Habitat? The vision was to enable human exploration missions to Mars and safely return the crew back to Earth. The mission was to design, develop a Mars Transit Habitat that would minimize the number of space shuttle launches. So the idea was to, one launch, be able to have enough capability for habitation to support the crew going to and from Mars. So our goals, we had several goals. One was to prove feasibility of using inflatable structures technology. Up to this point, it had been suggested, Langley had did some work. There was the Lunar Space-Time Extension Module. There was also a torus that was developed. But what was lacking was the technology of the fabrics to really enable that. So like the coming along of Kevlars and Vectran really allowed the use of fabric tensile structures in a way that would create a pressure vessel. So another goal was to launch in one launch, as I mentioned before, to enable human health and performance, the physiological and psychological well-being, provide sufficient deep space transit habitable volume for all 6 crew members, build and test in-house, so becoming a government furnished equipment or system, and provides the next generation of young aerospace professionals, engineers, architecture, and science with DDT&E experience, design, development, test, and evaluation, and incorporate ISS heritage hardware and system racks, which was a constraint, not something we wanted to do. But since there was already some racks in development, the idea was to move them from other locations on space station, like I said, that some of the habitation functions had been distributed throughout, and move them to a consolidated one area for the living area for the space station. And so from those goals, we had numerous objectives. The habitat had to fit in the payload bay of the orbiter. We had to prove feasibility of the habitat technology for micrometeor and orbital debris, which in low Earth orbit, orbital debris is a big issue. We had to prove feasibility, proof of concept of the structural integrity, that you could actually build something that large a diameter with a fabric structure and that it would hold. And the other thing being an inflatable, there was no aerospace standards set on the factors of safety. So what we used is what was being done in airships with a safety factor of 4, which is way beyond what station module of 1.25 or 1.5. The other thing we had to do is to feasibility of the technology on being able to package and deploy in space. So being able to package it up that would fit in the orbiter payload bay, and then being able to run it through a like through vacuum of space and cold soak it, and then actually deploy it. And so those were important objectives of the work that we were doing. The other aspect was to fully embrace and promote human-centered design as internal architecture, separation of living and working spaces, promotion of the psychological well-being, and also to provide radiation protection, to develop a storm shelter for the crew. And we also wanted to minimize the use of racks. So we came up with a pallet system, which has been picked up and used off and on over the years in many studies from the contractors. So the ISS TransHab, which is a little different from the Mars Transit TransHab, the purpose of the ISS TransHab was to provide an on-orbit crew with safe operating and living environment in which they may eat, sleep, relax, care for personal hygiene and health, and perform limited space station operations and management. So some of the functions that you would have in the Mars transit habitat were not in here because we were attached to space stations. So some of those functions are provided by space station, like air revitalization, water, fluids, the waste processing, power generation, et cetera. So what were some of the design drivers? The environment was certainly a design driver for an inflatable prototype, because inflatables really, to this point, inflatables hadn't been tested nor proven. And so there was a lot of skepticism about it. And the design, the environment is always an important design driver when considering designing and building a spacecraft. So you got to look at the micrometeor orbital debris, look at the radiation, understand the natural and induced thermal environments, obviously the pressure, internal pressure, operating pressure, look at and understand electromagnetic effects and grounding, how atomic oxygen may play upon the materials. So you got to protect that. And then contamination, look at plume forces as vehicles, visiting vehicles coming and going, and the plume heating from that. So our assumptions to the project were that it was to be placed on ISS in December 2003. TransHab would be connected to the port side of Node 3, so we had to develop ICDs with them. TransHab would be delivered to ISS via the Space Shuttle system, so that was the constraint, both mass and volume. That the ISS have a hardware available for subsystems and outfitting, that we would utilize that. ISS provides resources through Node 3, as I mentioned earlier, those functions of power, thermal, CNDH, water, oxygen, nitrogen, etc. And that ISS racks would be relocated into TransHab, the galley and the checks, the crew health racks and exercise. Human research facility would have 3 racks, would stay in ISS as baseline, but looking at impacts for locating in TransHab. New crew quarters would be placed in a central core around, within a water tank or water wall. So the focus there was to not have a rack-based crew quarter design, but something different. And the original crew quarters designs were all within a rack. And what we determined is that rack was really too small for a crew member really to perform well and sleep and so on. You could fit in there, but it really wasn't very much volume. And so later on, the crew quarters that ended up being developed, which I worked on later on as well, is that we created a bump out to get extra volume in those crew quarters. And the last assumption was the full body cleanser um, was maybe rack based or not. We weren't sure on that. So these were the TransHab functions for ISS. We had the crew habitation functions, we had the crew support functions. And as I mentioned, some of the other functions that you would find on the Mars Transit Habitat were part of the ISS functionality. And I'm not going to go through all these in detail, but you can see there's some key ones. Private sleeping compartments, food preparation, food consumption, storage, full body cleansing, earth viewing, very important, have windows, and then additional storage. And then you have the crew support functions, social gathering, meeting, private gathering, crew healthcare, exercise, housekeeping. You had some environmental control, distribution, collection, and processing. We had some internal power management and distribution. You had to have A and B power channels. Communications was important, storage, circulation, and then the radiation protection. So we developed a concept of operations really focusing on and trying to understand an inflatable habitat. What's it take to assemble it, to do the vehicle checkout, to then ship it to KSC, to perform the initial preparation and installation into the orbiter payload bay, then launch into space with the vibration and acoustics and so on, those loads that would be seen internal to the TransHab. Remove and install it on node 3, deploy the TransHab, then inflate it, and then complete any vestibule jumpers in those connections. The crew enters, and then you outfit. And the thing about the concept of operations, each one of these that show a black shaded area is additional layers of the concept of operations going into detail into each one of these. And I'll show you a couple of those as well. So the TransHab, like I said, had very strict transportation constraints. It had to fit in the shuttle payload bay. It needed trunnions to be able to lock into the bay, and it needed to be able to package in there. It needed a little bit of power and so on during flight as well. But the internal aspect, what was unique is that we needed the internal of the TransHab to be able to go to vacuum. Otherwise, it would try to inflate within the payload bay, which would not be a good thing. So this is a artist conception of Frasnito and Associates that worked with us at the time. The inflatable TransHab was located in node 3. It had nadir viewing or earth viewing, and so those were where the windows placed. It had protection. It had the micrometeoroid orbital debris protection, which turned out to be almost a foot thick. So given the environment, again, low Earth orbit with orbital debris, and given the size of TransHab, we had to design a micrometeoroid capability to protect the TransHab. And so, but if you were going to Mars or where there's micrometeoroid, but not orbital debris, heavy duty, big stuff like in low Earth orbit, the thickness of the the micrometeoroid orbital debris protection can be tailored and thinner and lighter. So this was the additional concept of operations showing the installation sequence flow. And this is really important for everyone. When you think about your concept of operations, you want to be able to walk through the entire sequence to better understand what's going on every step of the way, what functions are needed, what power, data, etc. might be needed, what are my structural interfaces. And it really helps you understand and drive out the requirements as well as the interfaces and design of the system. So I'm not going to read through this, but you can certainly walk through this yourself and better understand what it would take to install an inflatable onto the space station, the sequence of events, you know, every step of the way, the different activities that are required, from disabling utilities to in the orbiter payload bay, you know, the removing the TransHab from the cradle. You had to have a cradle system, and then maneuvering TransHab and capturing to node 3 calming berthing mechanism. But you bring it close, but you don't touch right away because you need to let them thermally equalize and stabilize before you bolt them together. And then you bolt the calming berthing mechanisms together. You perform a vestibule atmospheric check, then you node 3 vestibule, and then you partially perform some of the calming berthing mechanism, electronics, and insulation. Uh, Check out the tunnel, which was a pressurized tunnel on TransHab, make sure everything's okay, and then ingress into there and connect some jumpers. You want to connect your power, you want to connect your CNDH, etc. Once you get through that, now you can begin to turn some things on. You can start to activate and bring things up and start seeing how things are going inside TransHab. You have not even begun to inflate it yet. This is all just pre-check before you actually begin to deploy the shell. So this is the remaining aspects of the outfitting that would go into it, removing, completing the jumper cables, connections, deploying the fairing and flooring system, activating the fire system, ATUs, caution warning panels, activate the common cabin air assembly, get some airflow, get some movement going, and make sure and check out the pressure and atmosphere before you enter. And then you're able to open the hatch from the TransHab tunnel into the main and be able to ingress into level 3 in the core and begin to remove the different packaging that was in the core on those on the pallets or the shelves, and move those into the place. And I'll talk a lot more about the packaging aspect, but you can see that there's a lot involved in moving the different shelves into their locations and getting things connected, getting things up and running. So the difference being, this is a type 2 or class 2 pre-integrated, not pre-integrated, but inflatable or deployable habitat, compared to a class 1 habitat, which is fully integrated like a space station module, ready to go. So there's some work required to get it set up. That's the kind of the trade-off between a class 1 and a class 2 type habitat. The outfitting continues. There's a lot of work to do to get it all up and running. You can read through all these different aspects, every step of the way, everything that needs to be done, and getting everything translated and moved and installed and then connected. And then you do your verification and your checkout, make sure everything's working correctly. And then you're ready for habitation. This was our assembly flight timeline with the crew. So we had the orbiter crew, which was 5 crew members, and then we had the ISS crew, which was 3 crew members, as that's what it was assumed. And they each had a role and parts to play in the whole development or deployment of TransHab. And it was over multiple days. This was day 2 to day 3 when they were doing a lot of their activities. We had to develop all the specifications for TransHab. This was the proposed specification at the time. You had the space station 41,000 spec for ISS, which then has the ISS HAB requirements document. And then from there, you had the TransHab project technical requirement specification. And then from that, you had multiple specs that flow into your interface control documents, as well as your specific subsystems specs, your end item specs. So these were the documents. You had a level A spec, which was the ISS TransHab performance requirements. We had the TransHab baseline architecture document, the functional requirements document, and then the system specifications. And then we also had the ICDs, which were important documents to interface to both the space shuttle, to the SRMS, as well as Node 3. These are all very important documents. These were this is a partial list of our design requirements. Just I pulled out a section to show you some of the requirements or constraints. Circulate atmosphere, intermodule, circulate atmosphere, uh, intra-module, and then control general illumination intensity, etc. And you can see that there was numerous aspects of visual, validate commands, collect functional data, assess functional data, detect fire, and so on and so forth. And these were some of the requirements. And there's a lot more that involved the food systems, storing, rehydrating, heating, maintaining, refrigerating, etc. Use of potable water, and processing wastewater, which the rephase shall provide wastewater to Node 3 in accordance with Node 3 ICD. So we were not processing wastewater, we were sending it over to space station for them to process. This talks a little bit about the TransHab interface resource functional requirements, and shows how the interface of the requirements for warm nitrogen purge on the ground, and power. So this was in the ground processing aspect at launch. And then power and thermal conditioning only during launch for the orbiter. They need to provide power. And also then overpressurization valves and negative pressurization valves were important because, as I said, we needed TransHab to allow it to go to vacuum in the core. So the tunnel part was actually the only pressurized part during launch. And then it talks about all the ISS interfaces and the data, power, and so on that we're interfacing with for the orbiter and space station. This was our interface diagram for ISS to TransHab. Between TransHab and Node 3, we had wireless antenna that goes both directions. Structural and mechanical, so both sides have the common berthing mechanism, etc. We had data going back and forth, thermal going back and forth, audio, video, intermodule air, or ventilation. We had oxygen and nitrogen coming to us, wastewater going back to Node 3, potable water back and forth, electrical, we got our electric from Node 3, atmosphere sampling went back to Node 3, and then recharge and N2 and N2 were future add-ons or scarring. Sorry. So this was the interface diagram that shows the common berthing mechanism, and the blue ones were the ports or connections that we utilized for our connections to TransHab. And it shows the interface and all the different interfaces and labels and what it was, the functionality. So let's talk a little about the TransHab architecture. So it was designed with a vertical orientation. So it had 3 levels, and the 4th level was the pressurized tunnel. And the reason we had a pressurized tunnel is some equipment we needed to have operational during launch and during deployment. So some of the systems was put in here, but this area here went to vacuum during launch. It was packaged up. So we had equipment and shelving systems and inside the core, and then that stuff would get moved out into the space and allow for the outfitting of the TransHab. The other unique thing is with TransHab is we wanted an open to a large clear story space for the crew to feel that more openness and not being like they're living inside of a machine inside of a can. These were the ISS TransHab functions, as I discussed earlier. This is the water wall, and the crew quarters were in the core section. There was multiple ways to pass through the TransHab and to go in and out, but you had one way to get into space station. We had two windows built into the TransHab. We had the wardrooms seating and the galley area down at the first level. The second level had the crew quarters and the mechanical room in the back, which was closed off and separated. It could be run at higher temperatures, better for a thermal aspect and isolation of the noise of the equipment running. And then the third level was crew healthcare. It had the exercise equipment, had the checks racks, and then the fourth level had the pressurized tunnel, which had some of the power systems and the switching units. This was the inflatable shell, which was a multi-layer functional shell, and I will describe that in a little bit. Also, what was unique is we used inflatable outfitting compression rings that inflated a little bit larger than the TransHab, so that for attaching equipment or struts or flooring, that it was attached to this compression ring. That way, they were not attaching directly to the uh, bladder or the seal of the TransHab, creating any issues there. And then we had internal down below a soft storage array for using the cargo bags, cargo transfer bags. So this is a cross section, a plan view of level 1 showing the layout. We incorporated 2 racks. We had utility chase runs shown here with a hand wash. We had our soft stowage built in the back here, and then you had a clear pass through and this clear story here. So the galley was here, you pass through up through here. We had our utilities running vertically through the TransHab. These were the red is the longerons, and these were the shelf units. And we'll talk more about the shelf units, how they were used both during launch and then afterwards. This shows that kind of view of the areas. Back then, the CAD rendering systems were quite behind the times compared to where they are now today. So, but anyways, this was an assessment looking at the layout and how we might use it. This is level 2, the cross section, the plan view. And so the racks were moved out, and we were able to relocate the shelves. And the shelves created the framework for the crew quarters. We did have to run our utilities, and so crew quarter 5 and 6 kind of got cut down a little bit. From the utilities, you can see the water wall around the unit. And then we had the how the shelves with the pre-integrated equipment can be taken out of the launch configuration and placed into their configuration in the mechanical room, locking them into place and giving good, easy access for the crew members to service both sides of the equipment and then be able to connect it up to the rest of the systems. The other unique thing is that we left the flooring open in a couple spots to allow air to return air from the mechanical room for processing of the air and moving it through. This shows the private crew quarters. There were 6 crew quarters. There were about 81.25 cubic feet of volume. That was about 25% larger than the ISS rack. The rack was 64 cubic feet, but that was without the bump out. And I mentioned later on, we did design to use a bump out because the racks were so small. But these private crew quarters created that need for privacy for the crew, a quiet space to go to, sleeping area, a personal area that they could decorate as they wanted to. And it also had radiation protection. So in case of a storm, a solar flare storm event, the crew could go inside of here and be inside of here through most of it, and then go obviously out to use the bathroom and come back in or grab some food. This shows that kind of configuration. Also, it shows the original configuration of the shelves that would be during launch. Obviously, these get removed and placed around afterwards. This shows the back area, the Eclipse equipment room, how we utilize and move the shells after launch into their locations and made easy connections as well. And the interior of the TransHab had a scuff barrier or the shell wall to prevent any damage to the bladder system. Also, we used the idea of sound absorbent and fire retardant fabrics on the flooring and the ceilings and the walls for this equipment room. Level 3 was a busy level in that it was the exercise and also the medical area. So we had movable partitions. We had storage, soft storage in the back here, movable partitions where you could have private medical screening and activities there. You had your full body cleansing, which was either rack-based or not, and then the other checks rack, which had to do with the exercise equipment and monitoring the crew during exercise. We had the pass-through, so you had two ways to go up and in and out of the TransHab throughout the TransHab, but there was certainly only one way to go in and out into the ISS. And this is some of those graphics showing that layout. And we also use the shelves to create stability in the flooring system for the treadmill and the ergometer. We also built a mock-up. Myself and Constance Adams, who's a space architect, rest her soul, she's passed away, worked with us in helping to design the internal architecture and was instrumental in working with me and us on the architecture and the internal architecture. The other thing is we built a mock-up, a low fidelity mock-up, so people could get an idea and what we're talking about with the lightweight shelving and isogrid shelving system that was used during launch, but then relocated and used as part of the establishment of the outfitting for the TransHab. Oh dear. Okay, another aspect of this was that we had to build and test it. And this is off a little bit, so I need to skip that. TransHab spec, this is the overall width and length of the TransHab. You can see it was about 10 meters overall length, including the unpressurized air system. You got to have the air tanks to be able to inflate it, the pressurized node or the tunnel, and then obviously the level 1, 2, and 3. We shortened up level 1 about 7 feet, and then level 2 and 3 we wanted them to be about 8 feet, and the diameter overall internal diameter was about 25 feet or 7.6 meters, but external was about 27 feet. And the reason being, again, was the thickness of the micrometeoroid and orbital debris protection system. The actual restraint layer and the bladder system is only like a ½ inch thick of Kevlar and bladder. So you had an internal diameter of 7.6 meters, the package volume, the deployed volume, this rough concept of operations, and you have the whole system overall total volume when it's fully deployed. So the air system integration, the idea was to create air ducts or rings at each level that supplied the air to that location, that area, and then the return air would be brought back into the CCAs, which were in the mechanical room. So the idea here was to get good airflow and good air mixture and make sure everything flowed. And so we had analysis done, which looked at all this airflow and looked at how everything was connected, and we did pretty well. It worked out pretty well for us. So it was a bit of conventional architecture and Eclipse or our air HVAC design combined with our space systems, the common cabin air assembly, et cetera. This is a structural overview where we had the unpressurized cone. We had our trunnion system for putting it into the cradle to set it in the payload bay. And so you had to have these um, cradle trunnions to be able to fit it and support it. So what it became when it was laying in the shuttle payload bay, it became a big cantilever, a big beam, if you will. You had the core, which was longerons and the shelving units to create its structural integrity during launch. And then we had the aspects of the deployed compression rings and floor struts and so on that gave you the internal secondary structure. So the general structure configuration was that you had the multi-layer inflatable shell, which had multi-layer insulation blankets, the micrometeoroid orbital debris protection, the optimized restraint layer, and then redundant bladders with protective covering or scuff barrier on the inside. The central core had the two tunnels. It had the composite core. So we used composite core with integral water tanks. We used repositional composite isogrid shells as shown here. And that actually created a cruciform structural integrity during launch as shown on the left here. And then floor struts with fabric flooring that would be deployable to give you your floor areas. This shows that hard central core, which was very important to the success of TransHab and its design, the different aspects of things being folded up and packaged for launch, and how the shells were connected in to create, like I said, the cruciform aspect and the structural integrity of this, think of it as a large column or beam. Then this is the deployed internal structural overview. We had the inflatable composite compression rings. We had the core. You had some shelves that remained in place, but once you're on orbit, you don't need these structural shelves anymore, and they could be removed and reused throughout the TransHab in various ways and various forms, providing stiffeners, providing rigidity, to the overall internal architecture and secondary structure. As I mentioned earlier, we looked at using these isogrid shelves as being able to package our subsystems on there on both sides of the shelves, making it easily to package, but then remove. So life support systems, the common cabin air assembly, some of the avionics packaging, et cetera, we could pre-integrate onto the shelves, test them, check them out, and then place them into the core. This allowed us to really reduce the idea of racks and a box in a box in a rack, thus helping with the structural efficiency. So the shell of the inflatable was a multifunctional layered approach. And with that, with a multifunctional, multi-layer approach, then you can look at each layer. So you break the big problem into smaller problems, and then you solve those problems. Starting with the outside, we needed external thermal blankets to protect it. So multi-layer insulation and Kapton and so on, from atomic oxygen and thermal control. So you had the external thermal blankets. Then you had the micrometeoroid orbital debris shield. That was a multi-layer of ceramic fabric spaced out in a kind of a Whipple system to protect the Kevlar, to protect the restraint layer, Kevlar or Vectran. So the thickness that this ended up was really driven by the environment in space station orbital debris in a low Earth orbit. We had to incorporate the windows. Then we had 3 redundant bladders on the inside. So the restraint layer, or the Kevlar or Vectran, is what holds the pressure in. That's what does the structural job. The redundant bladders were made slightly larger than the restraint layer, so there was no pressure put on the bladders. The bladders held the gases in, but had no structural strength. They were pushed up against the Vectran or Kevlar of the restraint layer. And then you had an internal scuff barrier to protect the bladders. What was unique about TransHab is the restraint layer. It was a basket weave approach of crisscrossing the Kevlar straps, and we used 1-inch straps And we used a certain strap to give us a certain capability as far as that strap in tensile stress. So we would put and you could buy 12,000 K straps or 15,000 K straps, and that's how they rated them. And then we would test them to failure, and then we would weave these in and out and create our basket weave approach. And what we also had to do was we had to index and stitch them intermediately, otherwise the straps would shift and you would have a big problem when it came to folding or deployment. Also, this is a very manual, labor intensive, and many opportunities for human error. An alternative to this is to a continuous weave using something like you would think of as a tube sock, with using a mandrel and a continuous wound, um, um, a, a very dedicated design to that. And so it's an alternative way to manufacture inflatables. Part of what we had to do is understand and look at packaging and folding. So we devised, how are we going to do this? How do you package up? This has never been done before to this scale, this size. So our engineers were quite ingenious in that they basically said, okay, you've got your large inflatable, let's push in on it, creating these fingers, if you will, and then we'll fold them over. We had to be careful about folding too sharply at the corners because it will break the glass fibers of the Vectran or Kevlar, thus reducing the strength of the material. So, the blue represented the tunnel. We had our bulkhead, and so we pushed in every third gore, and then we were able to use a tool to help us fold over the gores and then wrap it and tie it. And it was quite ingenious, and it worked. It was quite clever, and it worked very well. We also had to look at how are we going to take these fabric straps, the Kevlar or Vectran, and then tie it to the bulkhead. And we developed a structural design that used clevis pins where we could bring the Kevlar straps around and wrap them and then sew them. So we had to develop and patent the sewing aspects of that strap. Then you brought in your bladders, and you RTV them, and you have a bladder plate or a bladder peel guard that it gets bolted and attached to that. And so your bladders are within here, and you use layers of silicone. You have your bladder, and we use bleeder cloth as well that we could then detect if we had a leak between any of the bladders. And your RTV was used to bond it all together. And that was the design, and it worked. And we tested it, and it worked. We used a similar approach to the windows. How would you get a window, put a window into an inflatable? Well, we used a concave curved frame. And with that frame, we had to bring those straps in and terminate them around the frame and bring them back and sew them together. And then you had your actual window integration from the interior covers, scratch pane, the pressurized panes, and the debris pane. This is the mass summary of the TransHab. You had your structural mass, the power management distribution. This is the ISS TransHab. So you remember, some of the systems are actually on ISS. This is only what was within the TransHab, ISS TransHab. We had environmental control, life support systems, and the flight crew equipment. So this had the launch mass. And then once we got on orbit, we had additional equipment brought in, the checks racks, the galley rack, et cetera. So you had your on orbit mass as well. These were the launch mass properties showing the details, the breakdown of the inflatable shell assembly, the core structure, the inflation system, and the launch trunnion assemblies, as well as the avionics that we had set up in the tunnel, environmental control systems that we launched on the shells, and our power management and distribution systems. It shows your growth allocation, which I believe we use 30%, and then our working weight with growth. And then, of course, you have to include fluids and air as part of the overall system, both dry mass and then your wet mass for launch. And then this is the on-orbit mass showing the additional equipment that was brought in. So your on-orbit mass actually ended up somewhere around 25 metric tons total. This is volume summary showing the different volume of the structure, both from a standpoint of packaged mass and then packaged volume. So you got an idea of how and what is being used. So anytime you do any kind of rack and stack of your masses, you do it with your volumes as well. So you can track your volume allocations and understand how much volume that your systems are taking up, which then when you have your total pressurized volume, you subtract your system volume, your equipment volume, your partitions, everything else that's taking up space, and you'll end up with your net habitable volume, which is what's left over, what the crew actually moves around in that volume and space. So one of the important aspects about the TransHab was prototyping it, the rapid prototyping and development and demonstration, proof of feasibility. So using a risk-based approach, we needed to develop and demonstrate. So we had to really think about what were the big risks to overcome the fear of inflatables. And trust me, at that time, many of the gray hair engineers were really against this idea of inflatable and fought us tooth and nail all along the way. So, and actually that was good. It made us stronger. It made us work harder to prove, because we really felt this was a viable option. When I started working at NASA in 1988, late 87, I was working and designing inflatables. I had interest of tensile fabric structures from Bird Air and so on from my time in Buffalo. But I had this interest in inflatables, tensile fabric structures, and I was designing, various inflatables with numerous folks at NASA, and people were kind of resistant and didn't believe that my concepts or our concepts, along with Mike Roberts, that would even work. And so part of this was really an opportunity for us to prove feasibility. So the three big areas was if the inflatable is hit by a micrometeoroid orbital debris, will it explode? Will it rupture? What will happen? And so we needed to mitigate that. Everyone thought it was a balloon. It was just going to pop like when you prick a balloon with a pin, it just boom. So we really needed to prove that. We needed to do impact testing. We need to develop an orbital debris protection capability. The other was we needed to show proof of feasibility of the structural integrity of the pressure shell, that the Kevlar strap idea could withstand the 27-foot diameter pressure, that hoop stress. And because this was a pneumatic structure, we were kind of forced into using a safety factor of 4, which is what airships use for pressure testing. And then we had to show that you could fold it, fit it into an orbiter payload bay, launch it, and then deploy it in a space environment. In other words, a vacuum test with thermal cold soak and vacuum, in which we would use chamber 8. So goal 1 was really that MMOD test. And like I said, because we were on space station and because of the size of the TransHab, we had a large area that would be impacted by orbital debris. And we had a habitat requirement that HAB shall have a minimum of 0.982 no probability of no penetration, PNP. And that really set forward the requirements for us to then go figure out how to solve that. And so we made coupons up with different ideas, and then we would take it to the hypervelocity gun that used to be at JSC, and we perform tests. We would shoot at 6 kilometers a second of different size particles. And then we kept doing it until we got a configuration where it would stop a 1.7 centimeter particle traveling at 6 to 7 kilometers a second. That's almost a 3/4 inch. That's way beyond what space station was designing their hard modules for. And we did it. Actually, Alan Alda had, when he was doing Scientific American Frontiers, brought his TV crew and actually witnessed and did part of the testing. And these were the coupons we made up. We used a open cell foam that could be vacuumed and sucked down. So we could actually compress this whole system down for packaging. And we did, and we proved it. We used ceramic fabric as our impact layers to really break up those impact particles. And so when it hit the first particle, it started to break up. Hit the second layer, it was now really starting to break up. And then the third and fourth layer stops it. And because you had this 3 to 4 inch spacing, that's the key. If it was an inch apart, it would zip right through everything. Or if they were just layered together, it would zip right through everything. Another aspect of this was the hydrostatic pressure testing. We had to prove that this large diameter could withhold this pressure, a 14.7 psi delta pressure. And so we focused on that restraint layer. We focused on the fabrication of that large diameter. We knew we didn't have to make the full height for the pressure test, and the core could be just a iron bird, hardcore, structural hardcore. So the focus was really on the diameter, not so much the height. And we hydrostatically pressurized it, because if you pneumatically pressurized it and there was a failure, it's an explosive energetic event. So hydrostatically pressurizing it, when it fails, if it fails, then you're just release of water within the tank. So you submerge this within the tank. And that was the key. And we did have a failure the first time. And so we had to build another one. And we ended up finalizing, and we brought it to near 60 psia, and we held that for 5 minutes. We didn't take it to destruction. And that proved the feasibility. And here shows some of those tests going on. The unit being readied and lowered over into the NBL, and then the pressure filling it with water, and then overfilling, obviously, to get the pressure. So we did 2 units. The first one was to 30 psi, where we had a failure in one of the seams along the edges. And the second one we took to the 60 psid, and it held, and it performed and proved the feasibility of using Kevlar straps to create this large pressure vessel. Our third goal was this full-scale development, packaging, thermal soak, and test in a thermal vac. And so we, again, we use a structural core, an iron bird, if you will, creating the support stands. And then we had to build the whole inflatable shell system, all the layers, the restraint layer, the bladder, triple bladder, the MMOD layers, and then actually be able to pull it to a vacuum, suck them down, and then wrap it up and be able to show proof of feasibility there. So this was the full scale unit. This is just the restraint layer with the bladders inside. They pressurized this to, I think it was 0.1 psi, so not even a full psi, a tenth of a psi, and it was rock hard. You could knock on it. It sounded like it was metal. And that was in November of 1998. And this shows it when it's not inflated, excuse me. This is the unit here in the chamber, showing it inflated. Packaged up. We had to have support restraints and cables holding up because of the weight of the system. Obviously, this would be done in zero gravity, so we had to simulate part of that zero gravity for the capability of this. And we did. We packaged it up. This shows it in its package format. not packaged, but deployed format before we did the packaging and folding of the shell. We put the gore layers on. These are the micrometeoroid. They do not take pressure. They're not pressurized, and they were pull a vacuum on them. That's why they're thinner. And then we were able to actually put those gores on in place, and then get it ready for its packaging. This shows the unit all packaged up, supporting the chamber A test. And then we actually did our thermal cold soak in a vacuum. And then we did the actual deployment, and it worked. It worked beautifully. We had to develop a strapping system with cutters, pyrotechnics that would cut the straps and allow it to deploy and then inflate. And this shows the unit just before Christmas. So in summary, TransHab started out as a Mars transit habitat. And then 1997, and it was so well liked that NASA headquarters and JSC decided to build a full-scale unit and to do the technology development and move into rapid design and testing to prove feasibility in 1999. In the year 2000, it was canceled. Congress and a aerospace company lobbied Congress they felt it as a threat to their livelihood or their work for the habitat module. So Congress and everyone canceled TransHab. So that was it. We were done. 2000, we had made progress. We had made collaboration efforts with Alenia. They were going to work with us to continue and build the actual flight unit. But that's the end of that. So we developed those engineering test units. We tested 3 important high-risk areas people had concerns with, and we mitigated those risks. We had proof of concept that inflatable structures could be used as an alternative for space habitats. We revolutionized how the aerospace industry thinks about space habitats, and we just demonstrated how human-centered design and human system integration is important to the internal architecture of space habitats. Thank you very much for your attention. I appreciate your time. I hope this was informative to you. Thank you so much.